All right, so we are looking at position, velocity, and acceleration. Let me pull up my handout here. All right. One of your best friends from Calc 1 and Calc 2 last year, right? You missed them. All right, let's see what we got. Smiley face, make sure the pen is working. There we go. All right. All right, so we're going to look and kind of reunite with some old friends. We're going to look at position, velocity, and acceleration, but we're going to look at it from a vector perspective. So our position vector is going to be r of t, our velocity vector is going to be v of t, and our acceleration is going to be a of t. So they are going to have multiple components, typically 2 or 3 for our case. Okay, so kind of just some basic definitions. Think of your position function as a particle moving through space. So we're going to consider r of t, which has been our space curve up to this point. We're now going to think of it as a position function of some particle moving through either 2D or 3D space, depending on the problem. And so we're going to be denoting the position vector as r of t. And we can define the velocity vector by kind of thinking about our definition of a derivative that we talked about in terms of vectors. So let's consider the quantity, which is being given by this blue vector. I'm going to just put a portion of it right now from P to Q. The part from P to Q would be your displacement vector. So if you trace out your 2 position vectors to the initial point P and the terminal point Q, r of t plus h minus r of t is just measuring the 2 different vectors to your final position and your initial position and taking the difference. So this is typically what we would call a displacement vector. Now, when I scale it by 1 over h, which is what I'm doing here, think of it as multiplying it in front by 1 over h. Think of that as like a time interval. Now you're looking at that displacement over a certain amount of time. What that's going to do is it's going to scale the vector outwards now and make it longer, because we're going to want h to eventually approach 0. So this giant blue vector that you see that I'm highlighting in yellow is going to be think of it as like your average velocity vector. As we let h tend to 0, as that distance between P and Q gets tinier and tinier, I'm going to highlight a new vector I'm going to do kind of like, I guess, let's see, what could I use? Let's do it like a lime green. This lime green vector that you see would end up being my velocity vector, which is going to be basically your tangent vector to the curve. So lots of intuition for how we've already seen this type of stuff going on. The tangent vector really now represents your velocity vector, and that difference quotient really represents your average velocity. The difference between the red vectors would be your displacement vector. Okay. So think of this, again, this is measuring the size of the displacement vector, aka the numerator, per unit time, which is your denominator h. This is a small change in t. So this would represent your average velocity, and on some of your WebAssigns, you're going to have to compute that. Okay. If we let the limit of h go to 0, so as the 2 points start to converge closer and closer to 1 point to produce that tangent vector r prime of t, that r prime of t, now we're going to think of as the concept of a velocity vector, v of t. Okay, so velocity vector you should be thinking is the tangent vector that we've already seen. We're just giving it a context now. Notice it will always point in the direction of the tangent line, or in the direction of motion. So it still moves with the motion of the curve, just like the tangent vector did before. Just like last year, you defined speed as the absolute value or the magnitude of velocity. I'm going to call it the magnitude now, since we're dealing with a vector, not a scalar function. So your speed is going to be the magnitude of your velocity vector. Another way of thinking about it is the rate of change of your distance with respect to time. Typically, we'll use s for distance, like arc length. Rate of change of distance. WRT means with respect to time. So it's the derivative of distance with respect to time. It is the magnitude of your velocity vector. The acceleration is defined very similar to how you defined it in Calc 1. Now we're dealing with vectors. So the acceleration vector would be the first derivative of the velocity vector, or the second derivative of the position vector. So let's look at an example. A particle moves along a curve C given by position vector. So this is your space curve, 2 sine t over 2, 2 cosine t over 2. So we're going to deal with a plane curve right now. I guess I said space curve. This is more of a plane curve. We're dealing with a two-dimensional vector. It looks like it's a circle. Find the particle's velocity, acceleration, and speed at time pi over 3. So I'm going to start with velocity, find v of t, and then I'll plug in pi over 3. Find a of t, I'll plug in pi over 3. Find the speed. Sometimes the speed ends up being constant, so we might not have to plug in pi over 3, but we got to look at the specific problem and see what we got. So if I do v of t, I'm going to take the derivative of my position. I'm going to end up with, this is going to be r prime of t. And you can compute derivatives off to the side if you want. We're going to have some chain rule going on with the t over 2. We're going to have 2 cosine of t over 2, and then we're going to have to multiply by 1/2 because of the chain rule. So the 2 and the 1/2 will go away. So I end up with cosine of t over 2. Taking the derivative of the second part, we're going to have chain rule again. Derivative of cosine would be negative sine. So negative 2 sine t over 2, chain rule times 1/2. 2's go away. So I get negative sine of t over 2. Okay. So there's my velocity. I want to evaluate it at pi over 3, so I'm going to do that. V of pi over 3. If I plug pi over 3 in for my time, I'm going to get cosine of pi over 6. And I'm going to get negative sine of pi over 6. Notice it's a vector. It's got 2 components. So this is going to give me root 3 over 2 and negative 1/2 would be my velocity. It's got an x. It's moving in the x direction at a rate of rad 3 over 2, and it's moving in the y direction at a rate of negative 1/2. You could do acceleration or speed next. It doesn't really matter. I think I'm gonna, what do I want to do? I kind of want to knock out the speed because it's directly connected to the velocity. So I'm going to do the speed. The speed is going to be the magnitude of the velocity vector. So I'm going to take the square root of the sums of the squares of my components. So I'm going to get cosine squared of t over 2 plus the sine squared of t over 2. And notice the argument is the same. You're taking the cosine squared of the same angle and the sine squared of the same angle. This is our favorite Pythagorean identity. Sine squared of some angle plus cosine squared of the same angle. In this case, the same angle is t over 2 would just be 1. So this is the square root of 1. Constant speed. We have a constant speed for this particle. Last but not least, let's compute the acceleration of our particle. This is going to be the derivative of the velocity or the second derivative of the position. So I'm going to do my chain rule again on this green vector that I'm circling. We're going to get negative 1/2 sine of t over 2. And we're going to get negative 1/2 cosine of t over 2 with the chain rule. Plugging in pi over 3, I want to figure out what the acceleration of the particle is at time pi over 3. This is going to be negative 1/2 times the sine of pi over 6. Negative 1/2 times the cosine of pi over 6. So I'm going to get sine of pi over 6 would be 1/2 times negative 1/2 would be negative 1/4. Cosine of pi over 6 would be rad 3 over 2 times negative 1/2 would be negative rad 3 over 4. Again, we want to give exact answers in the problem unless they tell us to use decimals. That would be the expectation on a quiz or on a test. Okay, so kind of here's our 3 pieces. This is our velocity at pi over 3. This is our speed at pi over 3, but actually it's our speed no matter what time we're given. The speed is a constant 1. The acceleration at that time is negative 1/4, negative 3/4. Okay, part B, we want to show that a of t, the acceleration vector, is orthogonal to v of t. In other words, the acceleration vector and the velocity vector are perpendicular. They form a right angle with each other. Okay, one thing I want to say about this is not always true in general for every single position function. It doesn't work the same way where we talked about unit tangent and unit normal. The unit tangent vector and the unit normal vector always will be orthogonal to each other because that's how they were defined. This is going to be an always. This is a sometimes. The velocity and acceleration may or may not be orthogonal. Here's the key. If the acceleration is constant, then you are going to have the acceleration vector be orthogonal to the velocity vector. And that goes back to a theorem that we learned, I think it was way back in like 13.2. We had a theorem that said that if r prime is constant, this is, I'm going to put because, this is if r prime is constant, then r is always going to be orthogonal to r prime. So in our case, take r to be the velocity. So in our case, we're letting v be our not trying to confuse you with position and velocity, but pretend this was you're using the specific case where we're interested in v. V prime is constant implies that v prime is going to be orthogonal to v. So in other words, the acceleration is going to be orthogonal to the velocity. Again, this is only when the acceleration, I wrote it wrong. Sorry. No, I didn't write it wrong. Sorry. Yeah, when the v prime, magnitude of v prime, in other words, the magnitude of the acceleration is constant. Okay, sorry for the pause there. Let's continue here. Okay, we should be back. Okay, so yeah, to sum that up, your acceleration and velocity are only going to be orthogonal if the acceleration magnitude, the magnitude of the acceleration is a constant. So just make sure you check that. So we need to prove that a of t is orthogonal to v of t. So all we're going to do, tricks from the past, how do we prove things are orthogonal? We're going to show that a of t dotted with v of t equals our favorite number, 0. Dot products equaling 0 means that vectors are orthogonal. Notice I'm going to do this for general times t. It means it should work no matter what the time is. It should always be orthogonal in this case. Okay. So what was our acceleration vector? We're going to take our results from before. So we're going to take negative 1/2 sine of t over 2, negative 1/2 cosine of t over 2, and I'm going to dot product that with the velocity vector, which was cosine t over 2. And let me get my other piece, negative sine of t over 2. Make this kind of go off to this side comment. Okay, taking dot product, we're trying to show it's 0, so we can't use it at 0. We got to get there. We're going to get negative 1/2 sine t over 2, cosine t over 2, and then we're going to get plus negative 1/2, or no, plus, we're going to have a negative times a negative is a positive, so plus 1/2 sine of t over 2, cosine t over 2. And now we can see, like terms, we got a negative 1/2 and a positive 1/2 with the same ending. There's our like term. This gives us 0. So therefore, a of t is orthogonal to v of t. That was the goal. Okay. Just to kind of convince you though, let's just make sure, I want to show you that this works out because of the fact that the acceleration is constant. So if you take the magnitude of the acceleration in this case, I'm going to take the magnitude of this vector. The magnitude, so this is just a way to kind of confirm here, the magnitude of the acceleration would be 1/4 sine squared t over 2 plus 1/4 cosine squared of t over 2, which ends up being sine squared plus cosine squared is 1. So this would be the square root of 1/4, which is 1/2. So we do get constant acceleration. So no matter what time value you're dealing with in this example, the velocity and acceleration will always be orthogonal, but that is not always the case. That is a sometimes. Okay, I'm actually going to show you on the animation. Where'd my animation go? I linked this for you also. It's on the Google Classroom and it's in the chart on the homework doc. If you go to different space curves on the velocity and acceleration animation, the purple vector is the velocity vector and the orange vector is the acceleration vector. You can kind of see as the animation moves, it's not always forming a right angle, right? There it's acute, there it's obtuse, there it's acute. You can play with different space curves. I have curve 2 set right now. If you go to curve 3, let's animate this one. This one moves a little bit more slowly. And now it looks like you have to go through the computations for this one to see if the acceleration is constant. It looks like it's forming a right angle fairly consistently with this example. And that looks kind of acute. So you can see the angles are changing. Let me look at a different one here. This one looks like a swan. Yeah, clearly not forming a right angle all the time. Obtuse, acute, acute, acute. Yeah. So you can see it's not always going to be orthogonal. So this animation hopefully convinces you. So you got a couple different ones you can play with. A couple applications of when you would use this. You can read about if you're interested. Skiers would be interested in knowing, when they go down a jump, the velocity and acceleration of the vectors would nearly be parallel. Laboratory technicians use a device called a centrifuge. The velocity vector for any object in a centrifuge is always going to be tangent to the circle of motion, whereas the acceleration will always be center seeking and point towards the center of the circle. The most interesting one I think they had listed here was a skydiver. Gotta, pull your parachute at the right time. You got to be very cautious because sometimes the velocity and acceleration magnitudes might be very great from the jump. Once you open the parachute, the acceleration vector is actually going to move in a direction opposite to the velocity vector. And when those two very large magnitudes counteract each other, that's what kind of causes you to jolt when the parachute opens. So lots of cool applications of these vector valued functions. Okay, some quick practice here. Maybe you want to pause me and try this out yourself before I put the solution up. Okay, so if you had time to try this out, velocity, let's try it here. Velocity is going to be the derivative of the position function. So we're going to get 2t, we're going to get 4e to the 4t. This one requires a little bit of product rule, so I'm going to do that off to the side. d dt of te to the t. First times derivative of second would be te to the t, plus second times derivative of first would be e to the t times 1. So te to the t plus e to the t. So there's my velocity vector. They asked for acceleration and speed. I'm going to do speed next just because I like to do that second. This is the magnitude of the velocity vector. Square root of the sums of the squares of the components. So we're going to get square root of 2t squared plus 4e to the 4t squared plus te to the t plus e to the t squared. Clean it up a little bit. You don't have to FOIL out that last one. That would get real messy, but at least clean this up. This would be 4t squared plus 16e to the 8t. And I'm not going to FOIL this one out. There's no need for that. That's just messy algebra. That would be a waste of time. Okay. So that would be my speed. So far I got velocity, I got speed. And we're going to do acceleration. That's going to be the derivative of my velocity vector, second derivative of my position vector. First two components, pretty easy. We're going to get 2. We're going to get a 16 because of the chain rule. So we're going to get 4e to the 4t times the 4 from the chain up top, 16e to the 4t. And then this looks awful, but it's actually not because you already actually took the derivative of te to the t up here. The derivative of that first portion right here that I'm going to circle in green is this right here. So it's almost kind of like a recursive derivative going on here. te to the t plus e to the t would be the derivative of that first part. And then you're going to tag on an extra e to the t. Since we're adding on e to the t, derivative of e to the t is e to the t. So these two combine into 2e to the t. So I'm going to clean this up. We get 2, 16. I'm running out of space. I think I'm going to write this. Let's see. Where do I want to put it? You know what I'm going to do? I'm just going to erase this part and write 2t. So I'm taking e to the t and e to the t, adding them together. I would get 2, just to save myself some space here. 2e to the t. That would be the simplified version. There's my acceleration. And from that last component, if you wanted to factor out an e to the t, as long as you keep it inside the brackets, you could. Okay, yeah, they didn't ask us to evaluate this at any points in particular, so we're good. All right, now we're going to use the initial condition type problems that you did in calc last year. We're just going to add on another component since we have 3 dimensions. So a moving particle starts at an initial position of 1, 0, 0. So I'm going to highlight that initial condition. R of 0 is 1, 0, 0. The particle has an initial velocity. It's moving at, according to the vector, 1, negative 1, 1. So I'm going to write that in bracket notation. That's my initial velocity. And the acceleration function at any time is given by 4ti plus 6t plus 1k. We want to find the velocity and position at time t. Okay? So remember the relationship. Velocity is or acceleration is the derivative of velocity. So the first thing I would have to do here, a couple things. Before I can get position, I'm going to have to get velocity. How do I get velocity? Well, to get velocity, I'm going to have to integrate the acceleration function since I'm going backwards. So I'm going to take the integral of a of t. And we've done this before outside the context of velocity, position, and acceleration. We did this with just general space curves back in the first couple sections of chapter 13. Now we're just giving it a more applied context. So this should look fairly familiar. Those constant vectors are going to come back into play, those ones that we called C, C1, C2, C3. So we're integrating 4t, 6t, 1 dt. Come over here. This would give me 2t squared, 3t squared, and if I integrate 1, I get t, plus some constant vector c, which is going to have 3 components. I'm going to call it c1, c2, c3. So this vector right here is my constant vector. And this is equal to v of t. I'm going to use the initial condition so that I can actually solve for my constants. So using that v of 0 equals 1, negative 1, 1. I'm going to put in zeros for every t that I see. So I'm going to end up with 1, negative 1, 1 equals, this whole thing is going to turn into zeros. So really, I'm just going to be left with my constant vector. So now I can go back and find the actual velocity vector. The velocity vector is going to be 2t squared, c1 is equal to 1, so plus 1. C2 is going to be equal to negative 1, so 3t squared minus 1. C3 is going to equal 1. So I'm going to get t plus 1. Okay, so I have found one part of what they asked. I found the velocity vector. And it was so much fun that we get to do it all over again. Are you feeling the deja vu? To get the position at time t. How do I get position? Well, velocity is the derivative of position, which means for round 2, in order to recover the position function, I'm going to have to integrate the velocity vector. So we're going to integrate 2t squared plus 1, 3t squared minus 1, t plus 1 as a vector. Same idea, come over here. We're going to get raise and divide, 2/3 t cubed plus t. 3t cubed over 3 would be t cubed minus 1t would be t. And then we're going to get t squared over 2 plus t. Don't forget you have another initial condition to use, so you're going to have another constant vector. I'm going to just use d1, d2, and d3 since I've already used c's. So this is some new constant vector, which we're going to use this initial condition now for position. We're going to use the fact that r of 0 is equal to 1, 0, 0. So using r of 0 equals 1, 0, 0, we can recover the actual values of d1, d2, and d3 to make the final position function. So we're going to get, this will tell me, putting zeros in, this whole thing is going to wash out and become 0. This is going to become 0. This is going to become 0. So I'm going to get 1, 0, 0 equals d1, d2, and d3. So my final position function, I'll write it in blue, would be 2/3 t cubed plus t plus d1, which we just found was 1. The other ones are 0, so these two don't really matter. So I'm just going to get t cubed minus t for my y component, and I'm going to get t squared over 2 plus t for my z components. And that would be my position function. I could now use it to evaluate the position at any time that I want, if they asked. And I think on WebAssign you might have something like that. Okay. Last application I want to show you, this relates very nicely to Newton's second law of motion, which you may have learned about a little bit more in your physics class if you've taken physics. So in general, we've seen this now. Vector integrals allow us to either recover velocity when we know the acceleration, or they might allow us to recover the position if we know the velocity. It has to do with that integration or differentiation relationship. One other thing we can use is if we know a force acting on a particle, then we can actually find the acceleration using Newton's second law of motion. And you may have learned this in your physics class at a very basic level as FMA, F equals ma. We're going to deal with vector versions of this, though. We're going to deal with force as a vector and acceleration as a vector. Okay. So the vector version of this law states that if at any time t, we have some force vector, we'll call it f of t, acting on an object with a mass of m, that is a scalar. So looking at the equation here, this is a vector. The mass is going to be a scalar. Also, it's mass, so this also needs to be a scalar that's greater than 0. You cannot have negative mass. The force acting on that object of mass m, producing an acceleration with a vector a of t. Okay, so this is also a vector. Is related by the equation force equals m times a of t. So basically, the force vector is a scalar multiple of the acceleration vector, if you think in terms of some of the concepts we talked about in class. I'm going to show you a real cheesy joke. You might laugh, you might not. I think it's kind of funny. If you look at the one on the left, it says, unbeknownst to mankind, animals have known the laws of physics for centuries. Take this sheep right here. Look to the right. Tell us, what is Newton's second law of motion? What does it say about force? And the sheep says, ma. LOL, right? Bah, ma. No, okay. Moving on. I hope you finished the video and are not thinking of ending it too early because that was such a bad joke. I thought it was fun. Okay, little side humor. Let's do one more example. An object of, what did I just do? Oh no. Move this guy out of the way. What did I do? Oh no. Somehow there's a little circle just in the middle of my screen here. I'm going to do this. Wrong one. There we go. Well, can't get rid of it. An object with mass m that moves in a circular path with constant angular speed, that is omega, that's the Greek letter, has a position vector r of t, given by a cosine omega t I plus a sine omega t j. Find the force acting on the object. So we want to find f of t. And we want to show that it is always directed toward the origin. Okay, so we'll talk about that in a little bit. Okay, so this kind of center-seeking force, if you think of the center of your circle, that's what this is, right? This is going to be a circle. It's parameterized with sine and cosine and the same coefficient of a. Okay. So this would be a circle. And they told us circular path. The center of that circle, it's centered at the origin. There's no shifts. So anytime we find a force that is center-seeking, you may have talked about this in physics. This is what we call a centripetal force. The centripetal force. Just a little background about omega. It's angular speed. In terms of kind of related rates that you talked about last year, really all that is it's how fast the angle theta is changing, where theta is the angle formed by, I'm going to draw a vector in green here. Here's your position vector we've seen in the past. This might be your r of t. Starts at the origin and it hits a point P on the curve. That's your position function that we've talked about. So the angle theta is going to be the angle formed between the x-axis and that position vector. How fast that angle is changing as time moves along, as that angle starts moving around that unit circle, that's what omega is. It's d theta dt. And you did lots of related rates problems with this last year. How fast is the angle of the camera moving, things like that. A lot of fun related rates. So that's just a little background on what omega is. It's called angular speed. Okay, so this object's moving in a circular path. Okay. So it's moving around the circle. We want to find the force and show it's directed towards the origin. Well, we know our relationship. Force is mass times acceleration. So let's compute the acceleration. We're going to need to take two derivatives. First, I'm going to get my velocity by taking the derivative of my position. So I'm going to get negative a omega sine omega t, and I'm going to get a omega cosine omega t. Using the chain rule, I've got an inner function of omega t. Remember, it's derivatives with respect to time. So omega is a coefficient. You are not treating omega as a variable. You are treating omega as a coefficient, meaning it's just some number. T is your variable, time. Okay, acceleration. One more time. Derivative of velocity, second derivative of position would be negative a omega squared. I'm going to pick up another factor of omega from the chain rule again. Back to cosine. And I'm going to get negative a omega squared sine omega t. So now we can compute our force. Our force is going to be mass times acceleration. Okay, plugging in a couple things here. This implies that force is, we're going to get, if I kind of distribute the m through, negative ma omega squared cosine omega t, negative ma omega squared sine omega t. And I'm going to do something. I'm going to show you. You'll kind of see in hindsight why it works nicely. I'm going to factor out a negative m omega squared just so that I can really focus on the sines and the cosines. And the a. And you'll see why this is nice. This is a cosine omega t, and this is a sine omega t. The reason I'm doing that is because that actually expresses this new force vector in terms of the original position vector we were already given. This right here is r of t. So I'm going to write this force. So this implies that force is equal to negative m omega squared. It's just a scalar multiple of your original position vector. So why would that matter? Well, what was the goal? So okay, at this point we found the force. Here's our force, great. And you could have honestly given this one right here if you wanted to leave that part of the answer. That's great. But the harder part of this is how do you show it's directed towards the origin? And that's why I did the algebraic manipulation here. Think about your position vector. Your position vector starts at the origin and always points outward. Your arrow will always be the tip of that point on the curve. Here's P. That's your position vector right here, R of T. Well, you're trying to show that the force is directed towards the origin, which means you need to show that the force is moving still along the position vector, but in the opposite direction. So you need to show that your force actually goes this way. That's your force vector. How do you do that? You show that it's a scalar multiple of the position vector with opposite direction. Now, how do I guarantee that this is opposite direction? It's because mw squared is going to be positive. M is greater than 0. W squared is clearly greater than 0. That tells you that coefficient mw squared is always going to be greater than 0. So therefore, this is always going to be some negative number scaling your position function. So it's always going to take your position vector. It might change the size of it, but it's always going to shoot it in the opposite direction so that it is center seeking or points towards the origin. So I'm just going to say, so the force acts in a direction opposite to the radius or the position vector, which was r of t. And therefore, running out of space, where do I go? I'm going to erase my pictures up here for a second. And therefore, points in a center-seeking direction toward the origin in this case, since the circle is centered at the origin. Okay, that would conclude my argument. It's just a kind of a cool little physics application. We'll do some physics kind of applications now and again in this class. And I think that wraps up day one. We will talk about the tangential and normal components of the acceleration vector next week. For now, you've got some WebAssign you can practice with. You'll have some time in class to practice with that tomorrow. And you've got a little bit left of your packet to wrap up before the exam next week. So hopefully you're on the home stretch and you're finishing up all the fun stuff about vector valued functions from chapter 13. Okay. Again, I am hoping you enjoyed reuniting with your old friends PVA, position, velocity, and acceleration. Happy mathing. See you soon.